doing that first. Which makes more sense than what you would do in real life.
Cool. Okay. Is there anyone that missed last time that's here now? All right. Cool. So from last time, one of the, I guess the most important things to remember is, I assume you all remember the gates. You could draw AND gates, NAND gates, NOR gates, etc. I kind of expect you to be able to do De Morgan's and 4-variable K-maps. Are we good with 4? So I found out afterwards that you guys were taught a different version of the K-map for 5 and 6 variables.
We were taught both.
What's that?
In my class, we learned both.
You learned both?
Yeah. We just got the.
Okay. Yeah. So probably just going to worry about 4-variable K-maps for this course. I don't think going forward I need to do many 6. Maybe there might be a lab or something, but I don't think it'll be on an exam. Did we make it through? I kind of don't remember because I teach 2 sections of this class. Did we make it to the turning AND and OR gates into NAND and NOR gates example? Did we finish that example or did we stop that example? Okay. So if we have this function, which we'll start right with, it must be Z. Okay, so if we start with this type of an example of a function, and we want to turn this into gates, it tends to be easiest for us to think of and or, especially because this is the kind of function that we'll get out of a K-map, right? We're going to get sum of product or product of sums, which are and or gates. So what we can see pretty quickly is, can anyone tell what the output gate of this is going to be? And, right? We've got 3 and terms. One of them is really easy. Which one's the easiest one? G. So I'm going to throw that in the middle. The next term? Yeah, so you're going to have an OR gate that's going into that. And it's going to be this pretty simple E, OR, F. Let me make sure I don't have any inversions. Okay. Now this one is going to be a little more complicated, but yep. What are our terms? Yeah. And what are our terms? OR gate. Great. So it's pretty straightforward to draw that in AND or. So if you recall, I mentioned this idea of universal gates. These are NAND, NOR. These are what's implemented on our FPGAs. So FPGAs actually are usually made almost entirely of either NAND or NOR. and you'll also see memory. If you get into like memory architecture down the road, it's NAND or NOR very often. So we want to turn this into NAND and NORs rather than ANDs and ORs. And to do so is fairly straightforward. So see if the measure more. What are the alternate forms of these? What can we do? What's an equivalent way to write each of these?
For the NOR, you can run basically an AND gate and put the knots or bubbles on the left side.
Absolutely. And for the NAND, it's the same thing. You just flip the gate type, move the bubbles. So both of those are equivalent. So if we go down here, we see an AND gate. We want to turn this into a NAND gate. And we do so by looking over at this, or NAND or NOR. And this one's pretty close to what we've got already. So what we do is we just throw invert at each of these. Now to make this equivalent, all you have to do is if you double invert, everything stays the same, right? Invert, invert. Now we have a NAND and a NOR. Or, sorry, a NOR and a NOR. And then, what do I do with the G? Yeah, I mean, we're going to say not it, or we can throw an invert into that input. Coming through, we need, again, to double invert to make sure that we stay the same, but end up with, again, another NOR gate. All right, what do I do here? Sorry. Someone?
I make it a NOR.
NOR, how are we going to do that?
Bubbles on the left side.
Yep, perfect. And then what do I do to C? And push another bubble down there. Boom. Now we've got nothing but NORs, right? So that's all this is. Hopefully you went through something similar in 2700. And that gets you from an expression that's product of sum or sum of products into universal gates. And if you want, all that you have to do is to flip the gate type. So we got all NORs. If you want all NANDs, I'm a little confused. I can't remember which one's which. One of them you're circling the ones on a K-map to write the equation, and the other one you're just circling the zeros, and you'll generate the two different types of logic. Okay. So now we're going to move on to what we call hazards. There are two types of hazards that we'll work with, and one of them is a static 1, and the other is a static 0. And what a hazard is something when you would like it to stay 1 or stay 0 as you change through states, but you get a momentary glitch, which glitch is not the right word because a glitch is actually a specific term for something else. You get a hazard where you're going to get the wrong value for a brief moment in time. Are we good if I erase this? So a very simple borderline pointless circuit that we could do to show this is this guy. And this is going to end up with what we call as a static 1 hazard. And these happen because these devices are real devices, right? They're not instantaneously changing. If I put the value here and it changes, there's going to be some sort of delay. And later we'll define this as propagation delay. That's what you're going to run into. So if it is currently 0, and then I change to 1, so I'm going from a 0 to 1 at A, what's going to happen is this 0 changes immediately, right? Because the A it becomes a 1. And then the 1 goes through here, inverts, becomes a 0. Let's see, what's a good way to draw this table? As the 0 goes from 0 to 1, the 1 goes high. This is still a 0 for a little while, right? Or sorry, this is a 1 for a little while. Sorry, because it's inverted. Because we were a 0. Go to 1. This 1 happens. This gets delayed and then becomes a 1. Or 0. Because we're inverting, right? And the output Z, though, is just going to stay, is going to react to this change quickly, right? So what is the output Z at Z when A is 0? Yeah, so if we're drawing just the normal truth table, and we have A and Z, and A is 0, that is 0. Yeah. And if A is 1, Okay. Both cases, we're sitting at a 0. And so, 0 transition to 1, you're going to have a 0 to 1 here. And a 1 to 0 there.
In the book, the static 1 uses an OR gate. Is that not an AND?
I have drawn this wrong. You are correct. I'm doing the static 0, which is why I got confused on myself. Thank you for pointing that out. Should we keep doing the static 0? Because this is the same issue. Sorry, both of them will have an issue, and I was seeing that this issue was incoming, and I was like, I thought this was supposed to be static 1, but this is okay. So there's going to be a window in time on this one where I have a 1 at this gate and sorry, I haven't run through this example and my brain's farting. I'm not a morning person. So let's puzzle through. So what we're going to end up with is this issue where there's a temporary change a quick change on this one, a temporary change on this one, and our output's going to end up glitching. And so now it's just a matter of puzzling through why that's going to happen in the timing. So if I'm going from 0 to 1 on the A, this happens quickly. Z. If there is still a 1 here, I have a 1 and a 1, what is the output? 0.
Going the other way, exactly from 1 to 0.
Yeah. And so now we're going to start at 1. So we're going to go from 1 to 0. that means this is going from 0 to 1 with a delay. So then we have a 1 here and a 0 here. What's the output? 1. Should that output ever be 1? No. So that's your static 0 hazard. Now, if I had done this correctly, like I intended to, and not confuse myself, and did this circuit, it's the other switch that you're going to run into an error. So rather when we're going 1 to 0, it's when you're 0 to 1. Now what's interesting and useful is on a K-map, you can actually see these coming. There's a very literal definition for when this happens, which I will read to you just so we know, and then I'll show you. So, they occur when the static 1, this is a static 1. The two minterms differing only by one input. So a minterm is, if I have a K-map, what is a minterm on a K-map? No, it's actually just one of, well, it is technically, in a way you're right. It is just one of these squares. So on the K-map, we want to start grouping things together, right? So like the good groups would be like that. But then what you end up with, so let's read this again, two minterms differing only by one input that aren't covered by the same product term. So product term literally just means the circle, right? Because we're building out the sum of the products, and each of the products is a circle. So now we have adjacent ones, adjacent minterms that differ only by one input and aren't covered by the same product. Meaning they're neighbors and they're not circled together. This creates the potential for static 1 errors. Now there is a solution to this, again, that we can use for the K-map. That's very useful. Is we can add an extra term that increases the complexity of the logic, but doesn't change the output. And all you do to do that is add an additional circle, in this case. So now they're joined together. That doesn't change in that OR, right? It's just one more OR term, or this happens. And what that OR term is doing is adding another path for the data to flow through when it hits this OR gate that won't cause a glitch. So it's adding complexity to the circuit in order to prevent these static errors. Neighboring ones that aren't circled. That's really all they're getting at. Static zeros, you're looking the other direction is when you're circling zeros. We'll actually close up with a similar kind of problem here. We'll get another look back at this with a little bit more of a complex circuit. And that'll bring in the idea of glitches, actually. That one's fun. So that gets us done with lecture 1, which I have posted last week's, or not last week's, 2 days ago's video. They seem to work out pretty well. So I'll keep doing that. If you guys end up ever watching it and there's something weird with the audio, video, anything like that, let me know. Hopefully we find out before someone is sick or we go online and make sure it's all working. Okay, so moving onwards, which is going to be, just so you're oriented in the book, that was section 1.5. We're going to just go through section 1.6 now, which is just the Review of flip-flops and latches. You guys remember your flip-flops and latches? What's a kind of, let's start with a latch. What's a simple latch? No types of latches? All right. So you've got SR latches, if you recall. Set, reset, right? Your flip-flops. Do you remember the types of flip-flops? E, JK, T, right? Those are your major building blocks. Now, when you step into flip-flops, we start going from combinational logic, which is what the focus of all these things is, to sequential logic, which, in a simple way of thinking about it, usually means that it's clocked, right? And things are going to happen one after the other, whereas with the gates we use, they change as fast as they can. With flip-flops, they don't change until you clock it, right? They don't care what's happening in between the clocks. So, if we look at some basic ones for the D flip-flop, just some basic symbols, right? They're always a square. What does this little flag symbol mean? Yeah, that's the clock input. D flip-flop. The D is funny because you'll hear D stands for delay, I think is what the textbook. It also stands for data. Then you have your outputs, Q and Q bar, right? That's your nice simple D flip-flop that worries about when the clock hits, and the clock can be either positive edge triggered, right? So positive edge means something happens on the rising edge, or negative edge triggered, meaning it happens on the negative clock. And in systems, which is what we're looking forward to, you are going to have both types of devices. The positive and negative clocking is useful to make two things talk to each other, because you can have one flip-flop load in on the rising edge, and the next flip-flop take the data output on the falling edge, so that it can pass along pretty quickly without having to wait for each of the clock. An SR latch. So these flip-flops are usually built out of latches, which are then gated. So you gate a latch, which gated really just means clocked, or it has an enable, and the enable functions as a clock. The SR latch is probably the simplest. Right, and then output to input. And you'll have a set, reset. Your book, for whatever reason, is calling it P and Q, which is kind of annoying. But your set, what happens if you assert set? P or Q? Because Q is real, or P is really Q bar, which is why I don't like the P, is because they're changing it around on you. That's 1, 0. If I do the reverse, I reset it to what? 0. Now there's an issue. What happens if I assert both of them? We don't know, they don't know. It's an undefined state. That could be anything from it picks one of those two, having been the most recent, and it sets or resets, and you're in unknown state. Or you can even end up in a situation where this puts out a 1, and then that puts out a 1, and it's this delayed oscillation, and you'll start going up and down and up and down, 1, 0, 1, 0, 1, 0, 1, 0. So you don't ever want to do set and reset at the same time. Now this is where they start doing like gated latches, which I think they have an example in, but I'm not going to walk through specifically on. But this set reset idea is a very useful thing because it holds memory. It remembers what it was, but it can have an issue. And we want something that remembers it, but we don't want all of these issues. So does anyone remember which one of the more robust flip-flops is? So the JKs, right? Those are very flexible and useful flip-flops. When you have barge this thing. So let's look at this JK flip-flop in terms of what it remembers. So we have two inputs and the clock, and we're just going to assume that the clock is going to happen and then it'll load Q plus. What is the next Q based on JK and current Q? Getting too big of writing. 0, 0, 1. So basically all flip-flops, if we're looking at zeros and we don't do anything to it, it's just going to remember a 0, right? The JK, if you don't do anything to Q, so Q is a 1, and you don't have anything asserted on either J or K, do you guys remember what that is going to be? The Q plus, the next Q. Say, I need you guys to speak up a little bit louder.
It's going to stay 1.
Yeah, it's just going to say 1. It's going to remember what it's trying to do. Okay, so Q is 0, and I have a K. What is the K doing? Does anybody remember what the K itself does? It's like a reset, yeah. So anywhere where you're going K, you're here, you're going to get zeros. Similarly for the J, what does the J do? Set. It sets it to 1. What happens in the JK when I assert both? Toggle. Exactly. So if it is a 0, it becomes a 1. If it is a 1, it becomes a 0. So that's the so if you assert K, it goes to 0. If you assert J, it goes to 1. And if you assert both, it toggles. Toggles. So if it was a 1, it becomes a 0. If it was a 0, it becomes a 1. And that's where we get the term a toggle flip-flop, which is really just a JK flip-flop when you tie the two inputs together. Should I do that example? We'll come back to that one. Okay. So pushing on with this review, do you guys remember state machines? FSMs, finite state machines. Does anybody remember the two main types that we'll refer to? Mealy and Moore, exactly. What is the difference between a Mealy and a Moore state machine?
One's outputs just depends on state, and one has state and input dependent output.
Yes. So one of them, specifically the Mealy, cares about the output cares about both the current state and the inputs. The more state machine only cares about what state it's in. The trade-off then is that the outputs have additional information on a melee, which in turn means that a more state machine has more states. So for most people, it is easier to think about more state machines because you're only worrying about what your state is in to determine the output. Melee have the advantage of being fewer states, so simpler to design if you were a robot, but we're not. So we're going to go through some examples, or an example of each of them, and we'll look at the system. But can anybody give me a good example? What's your favorite example of state machines that we encounter in the real world? Garage door opener. That's I ran into that with my other class, and that was the garage door opener. And the one we always used was the traffic light, right? Those are the two, I guess, the Utah school system's favorite state machines is the garage door opener and the traffic light. So right for the traffic light, it is red, and after some time it's going to go green and then back to yellow and then red. And you might have inputs that are a timer, a light sensor, or a crosswalk button, those types of things. And you're going to step through each of these states. So let's use something a little bit more complicated. We're going to have a system that wants to look for this pattern. That's all it cares about, is looking for a 1, a 0, and then a 1. Now, if you had a combinational circuit and all of this data at the same time, so say you had a long string of something and then a 1, 0, 1, in combinational logic, you could just wire all those up and then have some output that said, yes, it's there. But if you're dealing with serial data and you want to react as fast as you can, we're in sequential logic looking for this sequence of pattern and then outputting a 1 when we see it. So given an input, our output then is going to do this, right? Can't happen until here. But this is our first real chance that it can happen. We can see it, so it goes 1, 0, 1. So it still hasn't happened. We saw a 1, 0, 1. Doesn't happen. Did happen. Happened again, right? 1, 0, 1, 1, 0, 1. They can't overlap, that's allowed. So that's our output state. So let's go over the melee machine. So the melee, we're going to start in some state. I'll give you guys that much, right? We're going to start somewhere at S0. Now, from this state, in this system, only two things can happen, right? We can get a 0 or we can get a 1. What happens if we get a 0? Yeah, we don't really care. Zeros are boring. And what is our output? 0. So we note it like this. We get a 0, the output is 0. So if we get a 1, we're not staying in the same spot. And we're going to give it the next state. All right? And our output is still 0 because it hasn't happened. So now we're sitting here, we've seen a 1. What are the two things that can happen? Okay, so if I see a 0, what happens?
You see a 0?
Keeps going. You're going to go to new state. Because this state has no way of making an output high. So this is, it saw a 0, and the output is still 0. Zeros are good. What happens if I see a 1? Do I go back to the first? So I go back to the first,
Go back to the second.
and then I could actually miss one of the 101s because I spent a whole time going back to this state. I actually want to hang out here because that one that I just saw could be the first one in a sequence. So we're just going to hang out there. So S2, similarly, it has two different things that it can see. What happens if it sees a 1? So it output. It's going to give you a something over 1, right? So it sees a 1, it's going to give a 1. Where does the arrow go? Yes, exactly. It goes back to here because that could be the next 101. And then if it sees a 0, it's not helpful. So notice here is our one state. When we do the state change, we get a 1. So that's melee. More, we know, has to have more states. And that's because the state determines the output. Sorry, there's always this battle to make sure I don't cover up the board from this half of the room. Are you guys okay if I write this? Because this is like the perfect spot to doodle. If I erase this, sorry. Okay, so the more state machine, obviously we're going to start at state 0. There's not a lot else we can do. And it's going to do the same thing. We know that if we see a 0, we just don't care. And we know if we see a 1, we have to go to another state. So if we didn't, nothing interesting would happen. So this happens if we see a 1. Right? So now we're back in the same boat. If we see a 0, if we see a 1, well, it could be the same thing. And if we see a 0, we're going on to some new state. Now, this is where we start to get a little bit more interesting, at least a little bit different. Yeah, they walked through. And you can, I don't use this notation, I always forget until I look at the diagram. So their book notation is this for more state machines. Where you have the state and the output in that little bubble. Because you're not doing it on the transition, it doesn't care about what the input is, it cares about what the state is. So if you're in state 2, which state 2 is, it has seen a 1, and now has seen a 0. The two things that can happen is it can see another 0. What happens? So it's seen 1, 0. Yep, we're going to go back to state 0. If it sees a 1, we're going to move on to another state. What is the output there? So we saw 1, we get a 1. But now this state has to do something different, right? Last time we only had 3 states. We're up to 4. What does this state do if it sees a 1? Which state does it go to?
State 1.
State 1. And if it sees a 0? One, 0, 1. Oh, don't forget to label them. I think that's how I missed most of my points when I did exams, I forgot to write the labels. So that's melee and more. You have to have extra states to communicate what the output is, and then be very careful, because there are more, you could do a more complicated version of this if you kind of lost track of what you're doing that would still be valid. That could not necessarily reuse these states. You could actually have individual states for all the possibilities rather than you reusing states, and you generally don't want to do that. The reality is, in modern times, it's way less important than it was previously. So we think of Carnot maps or Carnot maps. I do not know how it's pronounced. I'm not going to pretend I do. The K maps used to be way more important than they are now. They're still very useful, but when you had 100 logic devices on a chip, reducing something from 16 to 10 gates or something would be hugely important. Now we have like 10 million devices. So if you have a couple of extra states, it's probably not going to matter unless you're in really high-speed systems. So it's still useful to know to do the right states. And you're less likely to cause some weird errors if you don't have extra states. Mealy, more. Oh, and that's the other difference that I forgot to point out. The mealy can change as soon as the input changes. The output state can change as soon as that input changes because it cares about it. The more has to wait until that next clock edge to update because it has to wait for a clock edge in order to change states. This book, starting on page 17, is where these mealy and more examples are. It goes on further and talks about how to use K-maps and the state machines to start drawing out the circuits. I am not going to go through that at this time until I look at the class. We already have so much to cover, I'm not sure I'm going to need to cover that. Just so you're all aware. Okay, so now we have these sequential circuits. We have these states. If we know each state needs to do something, we can go in and design these, and when we hand it off, if we have a good state diagram, whatever engineer we hand it off to has a good picture of what the machine is trying to do, and only has to worry about the individual blocks. And so there will be people in some large projects just draw the state machine and hand it off and say, I need these states and I need them to work in VHDL. We'll usually refer that to a systems engineer, but these are very helpful in design. I really can't emphasize the state machine useful enough. But once we have these state machines, we have to deal with the timing of these state machines. They have to talk to each other. You're not going to have one state machine, right? And you're going to have two different parts of your system. One of them is going to be control logic, right? It's going to be controlling what the system is doing. And then there's going to be the memory. And sometimes I'll refer to as the architecture or the data path. And so they're talking to each other, and you need to make sure they talk to each other at the correct time. Because if they're trying to have a conversation now, and some other part is a second behind, it's going to get confused. And that happens in systems because we're building really big systems, right? You have VLSI as a course here. What does the VL in VLSI stand for? Very large, right? We're not very creative with naming oftentimes in this industry, but part of the reason we use that very large is because if you have a signal generated on one side of the chip and you're sending it all the way to the other, there can be enough delay, and we call that propagation delay. This term, the book uses it exclusively as a term in the devices. So if it goes through an inverter, it gets delayed, and that's propagation delay. But it can also go through a wire that's really long, and that can be propagation delay. And you could delay a whole clock cycle or half a clock cycle, and suddenly if you have a control unit over here telling a memory unit over here what to do, they could get out of sync with each other when that control unit then tries to pull the data back from that memory unit. So we need to worry about timing on this. So another confounding factor, and part of this propagation delay issue, is that your clock edges are not perfect. So if I have a clock, I want it to look like this, right? but there's two major confounding issues in this in a real system. The first one we call jitter, which is where this rising edge of the clock and the falling wants to happen here, but it could actually happen anywhere in some window. So your clocks that are generated from something we call PLLs are going, that phase locked loop. The PLLs are going to have some specification for what their jitter is, and that's going to be that clock bouncing back and forth. The other one is that as you hook up more and more devices to a clock, especially if you don't use buffers correctly, you're going to start getting a lot of capacitance holding that down. And what does capacitance do to a system?
It makes it harder to change the voltage.
Yeah, it makes it harder to change the voltage. You've got to put more work into it, and it slows it down. So your clock edges then can start looking a little sad. The most extreme example I have of this is I was designing a camera system for a particle accelerator, and the way these camera works is they have this big clock that essentially it treats this, the negative voltage, as a bucket to store charge, and then when the clock switches, it pushes all that charge from here into the next bucket. But to do this in a particle accelerator, my clocks were minus 20 volts to positive 20 volts. And I was doing this at 10 kilohertz, and to drive all that capacitance, took between 1 and 3 amps of current. And my clocks really started to look like that. And so you already have a little bit of an issue on the transition of when is it a 1 exactly. We don't necessarily know. It'll be specified, but there's a little bit of a difference. So when we're rising, if we're coming up at a slope, right, because this never happens instantaneously, it could trigger here, or it might trigger here. And there is very often directionality to when it's changing. So on the upswing, it'll change from 0 to 1 at, say, that trigger point, but then on the way back down, it won't go back to 0 till here. And so if your clock is irregularly shaped due to excess capacitance, your timing can get really screwy. So when we have that and we're start thinking about clock timings, on a flip-flop specifically, you're trying to read in new data, right? So the D flip-flop. D flip-flop has new data coming in and it wants to output it at the Q on the next clock. So if I have the clock, I'm going to draw a new one, happening. And we know that this can move around, whether it's from too much capacitance or from jitter or from the slope, right? We have this idea of the data can change anywhere in this window or this window just fine. This is where you want to change the window. But before you change the data, to make sure that the clock jumping around doesn't hurt you, you need to have something called setup time, TSU. That's saying set up your data before the clock has any chance of happening. So you're going to see these specifications on flip-flops to set up your data to be ready to read it. And then these flip-flops don't record it instantly. So you could set it up and then change, and you're going to capture some voltage in between on and whatever your next data, which it might be okay, but if it's changing, it might not. So we also have TH, hold time. So those are your two setup and hold. And you'll notice this stops here because now I have hold time from the last one. So that's your timing. You're going to look at setup and hold time requirements of your flip-flops. So let's look at a simple circuit. You could consider this, I don't know, it's fairly trivial. But let's start out figuring out what happens in this system. Right, so we're going to start out, let's see. Let's start out by considering Q at 0. And your D then is going to be at 1. And your ideal situation then is that you're going to clock your D into Q, right? And it's just going to alternate 0, 1, 0, 1 as we're going to step through each of this. But this inverter has some delay. So then we're going to start slowly speeding up this system. So imagine that we're starting slow and everything is working fine. We've done our debug, looks great, and then we're like, oh, we have to speed up this clock a little bit. So this clock for this guy is ticking along. So we're going to say this is rising edge triggered, right? And so Q is going to want to pull in from what D is. So the clock happens. There's some delay in the flip-flop. So here's the clock. Here's Q. And Q is 0. So the clock happens. There's some delay. Then Q goes high, right? Then D's here. D is already high. The inverter sees Q go high, inverts it, making D go low. Right? And then it's going to start repeating that pattern throughout where this little bit of delay. Now this is all fine because everything is settled before the next clock, right? But if we do what I said and we slowly increase this clock, these delays don't get better, right? So now if my clock is happening faster than the D and Q can handle it, the delay that results from the flip-flop and the inverter is going to suddenly start causing errors in this. So instead of this regularly spaced, nice, smooth 1, 0, 1, 0, you're going to start getting 1, 1, 0, 0, 1, 1, 0, is it doesn't really know, it doesn't have time to set up or hold for the proper value. So we're going to go with an example that I figured out that I think is pretty good. Let me see if I'm going to miss anything. One term that I need to make sure. So if you have unequal delays in a system, a term for that is clock skew. S-K-E-U, clock skew is a term you should be aware of. And there's this assumption that happens every once in a while for students that if you have 6 flip-flops or so, they're all going to have the same delay. But the power supply distribution of an FPGA or any digital system is actually fairly complicated. And even small variations in that power supply can change the speed of these flip-flops. So a lot of difficulty in designing large digital systems is making sure that you can meet timing constraints. And you'll see this error all the time once you get into digital systems. I cannot meet timing constraints. And trying to puzzle through, that's kind of what it's talking about, where you have these different system paths that are kind of branching out and coming back together to talk to each other. And one of them will have like 12 inverters on it or something, and the other one has 2, and the delay through them is very different. So let's look at an example where they can happen even in an unclocked system. Okay, so here's your system. This, we're going to label a couple of wires just for clarity. That is right. So I have B and C, A and C naught. So let's start with this. And this is going to bring in, this idea of glitches. So a glitch is what's going to happen in sequential logic. So similar to our hazards earlier. This is really kind of a hazard slash glitch. So glitches happen repeatedly and predictably on a clock, essentially, is what you're looking at. It's in sequential logic. This is combinational, but this is, like I promised, we're going to come back to one of these hazards that is more interesting, and we're going to define everything as having all components have a 1 nanosecond delay. So it's almost like a clock system for simplicity's sake, and I'm going to have you guys go through this example. We've got, what, 15 minutes? So A is just going to stay high. B is just going to stay high. And C after 1 nanosecond is going to go from high to low on forever. Now, F itself. If I have two states that I care about right now, and one of them is they're all ones, A, B, C, and one of them is A, B, C naught. What is F in each of those cases? Start with A, B, C. 1, yeah. So that AND gate is 1 into the OR, so we know that that's going to be a 1 regardless of what else happens, right? Because we're ORing B and C. Now if we switch to ABC naught, what happens? What is the alpha value? Also 1. Looking familiar, right? Nothing changes. So we're looking for something to go wrong, otherwise I wouldn't write this glitch. So what I want you to do is walk through in essentially 1 nanosecond steps. You should only need to go for like 4 or 5. Walk through drawing the timing diagram for BC, C bar, AC, and ultimately F. And I'll give you, let's see how much time I can actually give you. I can give you 10 minutes to puzzle through that. If you're stuck or confused, you can ask questions, feel free. So, just to give a hint in case anyone's stuck. So C bar is going to be starting opposite of C, which is low. That happens and raises high. Right? Because there's an inverter in between C and C bar, so there's a 1 nanosecond delay. Yeah.
Should the C on AC, the C be non in?
Yeah, like your own chart about that.
Yep. Okay. All right, who wants to give me what AC bar is going to do?
It goes from low to high.
Low to high. When does it go high?
On the same time C does, doesn't it? Because one,
So he's saying the same times as C goes high. Anyone else think differently?
Cycle after.
1 cycle after the C goes high?
should be
After C naught goes low.
After C naught goes low.
Sorry, goes up. After C naught goes high.
After C naught goes high, yeah.
Yeah.
So that's going to trigger there. Okay, so what's F doing? We know it starts out high, and we know there's a little bit of delay in there at very least.
always stays high.
Does it always stay high?
Well, if you have a 1 nanosecond delay when it should flip down, it would flip one
So-
cycle after and then come back up. Yeah.
Yeah. So you get this one nanosecond where it's the wrong value, right? And that's doing some weird stuff, assuming the same delays are all there. And 1 nanosecond is really long. But this type of thing will really happen in systems, where you're going to have these kind of dynamic changes where you want it to stay 1 and it just doesn't. So next time, well, let's see, I've got a little bit of time. So next time we're going to talk about this idea of clock enables, which is a really obnoxious topic to try and talk about. And I don't mean like annoying, I just mean like it's hard to wrap your head around why you would do it. And so I'll try and figure out the right way to explain it, because so often it takes students a long time to puzzle through it. But I will prep that. For lab this afternoon, it will be short, I believe. If you have your own laptop with you and you want to install Vivado, so Vivado is the program that we're going to be using to program the FPGAs that we have. It's free and huge. I have set up the Lab 0 on Canvas, and it's just a slideshow. It's just going to walk you through the checkoff for the lab. Can I bring it? Actually, I didn't bring the FPGA, it looks like. On board, there's a counter, and all you're going to be doing is the first part of the lab is how to install it on your computer, and the second part of the lab is how to work with Xilinx the Vado. So if you used FPGAs in the past, have any of you used the FPGAs here before? So 1, 2, yeah. So what happened is there was an old FPGA that we were using. I've updated to new ones because we couldn't get the old ones because they're so old. We've had to update the software that went with them because the software to program the old ones is long past expired. So I've been working through redoing the labs. So this one, the point of this lab is just to familiarize yourself of how to actually get a program onto an FPGA. And you'll notice it does it by, there's a little counter on the FPGA board, and when its default load is there, it just sits and counts. It has 4 digits, I believe, and each of them count from just 0, 1, 2, 3, 4. You're going to load on a program that is a hexadecimal counter that just goes from 0 on up to whatever 4 digits of hex is. It's pretty straightforward. It could be really quick. We'll meet over in the other lab. If you have your own computer, bring it with you. We have 8 more computers on order for that lab. It's the one across the 127, I think is the number. We have 8 more computers on order for that lab, but they're stuck on a boat somewhere in, I don't even know where. They're stuck on a boat, so we don't have the computers there yet. So if you ever have laptops to bring, and you can install Vivado, it'll make it easier for everybody to work with it. And I'm going to be checking out the FPGAs to you guys. Probably today. I would like to do it today. There's just one complication. I don't yet have the USB cables for them, but they're the same USB cables as an Android phone would be. So I'll probably just give those to you because most people have one. If you don't, you can wait, and it should be here in a couple of days. You know how slow the postal system is right now. And we'll get that set up, programmed, running through, and that way we'll get at least this lab, and I believe next lab at least, before there's any real threat of having to go online permanently. I think Weber State students are doing better than what you're seeing in the news in a lot of places. I haven't seen any big parties happening yet, like in Alabama and such. So I think we've got a little while before anybody screws up too bad for us. But I want you guys to get familiar with the FPGAs before we send you off, and I want them checked out so that you have them so that we can complete the lab. Again, you can work with a partner in these labs. That being said, 4 minutes early isn't too bad. You guys are good to go. Unless there's questions, I will answer, of course.
You say if you cared if our lab looked blind or...
I do not care. As long as it is bound in there permanently, you can't just stick in extra pages. And do it in ink, make it clear, and if there's answers, circle them. This lab book is going to be really easy. It's just going to be my signature, more or less, because you just got to get it loaded. Yeah?
Do we need a dedicated lab book?
You do need a dedicated lab book.
Well, mine should be at my house at some point today.
Yeah.
Not gonna cause a problem.
No, today is not going to cause really an issue. I will probably give you, just hand me something that I can sign that you can upload, is all that will be. Yeah, this lab is just getting you familiar with the tool, because the tools can be overwhelming, so I don't want you guys to worry about VHDL and. Oh, how many of you don't feel confident at all in VHDL? I had from my other class that said it was bad, the previous VHDL. Okay, I will keep that in mind as I teach it to you. I will just assume that it's very limited
The
knowledge.
guy that I had in asking a question, he would just give you the answer instead of helping you.
It's been time, but Jake, you've been so much help matter.
Yeah, no, I can see that. Yeah, so I've been recently, because I know Verilog, and I've recently been going through the pains of VHDL, so I can sympathize with you guys
that
on
was
that.
like 2 or 3 years ago.
Yeah. Okay, I will make sure to do my best with keeping it.
I think 2700 is good.
Yeah, so that's how we'll start, because I just need you to know how to load it onto a program, which they make it way harder than it needs to be. So the new Xilinx Vivado I actually really like. I'll be honest, this is the first time I've used it in years. I'm an Intel person, the Altera boards, but I've been with the Xilinx all summer, so it's a nice tool, actually. The Vivado is. So. Thank you.
Yeah, man.
3-hour block for lab and
I did,
15 minutes.
and,
What professor was this? It wasn't Larry, was it?
No, it was Trample.
Installers.
Oh, okay, yeah.
But I know I was busy with a lot of other stuff.
Well, Larry and Trample had the same issue where they didn't want to teach, they wanted to research.
Yeah.
So, yeah.
Just letting you know, like, that my experience as far as code and stuff.
That's fine. I will assume you guys don't know VHDL, and I will answer it.
We're confused on this.
Okay. So I get C
You're a weaver, I only get like.
Right here,
yeah.
up to 1 nanosecond.
Yeah, so C, 1 nanosecond goes low, which means C bar, 1 nanosecond later, goes high.
Right here.
I was gonna say, my house would get like.
So then 1 nanosecond later, this gate is So it takes 1 nanosecond for this wire to this gate to respond, and 1 nanosecond for this gate to respond.
Like high because it's high, low.
Well, when I first gave this bar,
Dr. Rabowski was doing a class
The other one I feel like it's.
I don't think I have it.
Alright, let me find my
Said
notes.
last semester there was something that would be good. Your laptop's like, no, I don't think we have
Yeah,
anything this
I did.
semester. And then Dr. Rabowski was like, yeah, I think we do.
Yeah.
I mean, that's what I'm going in here.
Because when I did my notes, I wrote. So A and C starts out. I think I inverted this one is what I did, but it ends up being correct. You guys might have actually been the only ones that spelled that correctly. So if we have A and C naught, this is low, right? So starting out, we have A and C, right? So that means this is 0. Because C is 1, this is 0, 1, 0 is 0. 0.
Then you should just.
Yeah, that's just, it's just because it's an AND gate. Okay. Then, you're in a situation where you have to wait for that C bar to happen while this is all propagating through, right? So this is 1 initially because you have B and C. After 1 nanosecond, this becomes 0, right? So your B and C. 1 nanosecond after C changes, B and C drop to 0.
Because of the truth table. Okay,
Yes, because of the AND gate. Because you're here, you start out at 1, 1, and it becomes 1, 0.
Because of this.
Because of the C change. So this is independent. So we're going to consider 2 paths. So in the first path, B and C starts out at 1, 1, and goes to 1, 0. Just from changing C. You don't have to worry about the later. So what that means is the B and C is 1 and then 0, right? Because it's no longer AND. So that means this, which was 1, became 0. And so just from that path, this is 0, right? It's not true because there's no longer an OR. So this path is initially the reason that is high, and that reason goes away. This path initially is 0 because you have A and C bar is 0. So the output of this starts at 0, which means it's not contributing to F going high. But after 1 nanosecond, this goes high because C goes low, this goes high, the inversion. Then so that's what we're seeing here. C bar goes up. Then 1 nanosecond later, this gate gets to react, which is the AC bar. So C bar goes high, AC bar goes high. Get it?
I'm lost.
Okay. This goes 1 to 0, right?
Yeah.
Output is transitioning 0 to 1 because this inverts. That far at least makes sense?
do you mean outputs transitioning 0 to 1?
So when C is high, C bar is low. When C drops to 0, C bar raises to 1.
Okay.
So then this gate, but there's a nanosecond delay here. So that inverter output, which is C bar, goes, oh, 1 nanosecond, it changed. It changed. It takes 1 nanosecond to go, it changed, right? Like an accelerator on a really bad car.
So how do you know C changed?
Because that was my definition. So I gave you these 3.
Oh, okay.
That's why everything else is encoded. So this is defined, this is... Okay, so then C changes. 1 nanosecond later, this gate can respond. And A, C bar, suddenly is true, because A has always been true.
Yeah.
And C bar went from not true to true. Sorry, A is always true, right? Yeah. So that goes high, but it takes a long time for it to see that, because it has to go through this gate and then this gate. So that's why it takes all the way here.
Okay.
So once that goes high, this guy can go, oh, look, this is now 1. That means, or 1, I'm going to go high. But because the delay in this route from it going, I'm no longer true, and this delay being longer saying, now I am true, you get this brief window where it hasn't seen the other branch change yet.
Okay. That
Make sense now? Yeah. Good. Yeah, it'll be definitely something like this on an exam. These are fun. Okay. Thank you. Sneak peek week 5 for you. Yeah, this was all review for the 3610, which is in sequence. Come in if you're in this class. I should just open that door.